Hi everyone again. This is Introduction to Pvsyst third lecture. In this video section, we will continue from the point where we left. Actually, in the second video, we will start the orientation. We will start and finish the orientation part. And if you want, let's start without delay. In the orientation part, when we click the orientation part, it says, please choose the field type. It wants us to choose the type of the field. Whether we are dealing with roof, whether we are dealing with the ground-mounted system, or if we are dealing with roofs, whether it be a 2-tilted roof, 3-tilted roof, or is it a flat roof? It asks us that points, or maybe we can deal with, as you see, the tracker systems. In our case, we are dealing with several orientation. Several orientation means we are dealing with rooftop systems, but in our rooftop system, it is not a flat roof. We have some sides of the roof, and these sides have an exact tilt for itself. What I mean is, when we open the Google Earth, as you can see, this is the one part of the roof. This can be considered as one roof, and this can be considered as another second roof. These two roofs stay side by side, and for these two exactly same roof, for the one roof, we have two opposite tilted sides that coincide in that line, and this line called ridge. This is the ridge of the roof. And when we open the Pvsyst for the number of orientation, since we are dealing with the two sides of the roof, and we have two different angles for that roofs. We have two different tilts for that roofs. We will say the number of orientation, the number of tilt. In another saying, the number of tilt will be 2. And it asks us what are the tilt and azimuth values of these orientation 1, tilt 1, and the orientation 2, tilt 2. What are the tilts and azimuth values of these two sides of the roofs? For the tilt, how we can take the tilt information? Actually, this is going like that. Assume that we are working for an EPC company, and we are a project engineer. We are working on, assume that just like in our project, we are dealing with the two tilted rooftop systems, generally the rooftop systems. And firstly, our site managers go to the place where we want to construct our system, and they make a site survey. And in that site survey, they are calculating the tilt of the roof, and then they give that information to the project team. And assume that our site managers tells us that the tilt of the both sides of the roof, of the one roof, the tilt of the two sides of the one roof is, the two of them is 6 degrees. And as for coming to azimuth, we are encountering with a new term, azimuth. Before dealing with the calculation of the azimuth, let me explain what is the azimuth actually. What is azimuth? As we write to that point, actually, azimuth is the horizontal position of the sun, which expressed in a horizontal plane of Earth relative to a fixed position or a fixed direction, in our cases, mostly relative to a north. But what I mean with that complex sentence is that assume that or Earth resembles a sphere, just like in this image, or Earth resembles a sphere. And the 0 degree refers to the north, 90 degree refers to the east, 180 degree refers to the south, and 280 refers to the west. And assume that we are cutting this sphere right in the middle. And when we cut right in the middle, we will attain a flat plane, as you see, flat surface. We will attain a horizontal plane, flat horizontal plane or surface we will attain. And assume that we positioned itself and assume that we are panels, we positioned itself to the point which is right as U. Let's assume that we positioned ourselves to that point. And it says, in order to calculate the azimuth angle, it writes, in order to calculate the azimuth angle for something like solar panel orientation, we can start from north as a fixed point and measure the angle clockwise direction to the point of interest. What that means with that sentence is that as you can see, it is the position of the sun in that image, and we are at the point which is marked as red. In order to calculate the azimuth, first we should know the points where our sun expressed in horizontal plane. In order to find the place where our sun expressed in the horizontal plane, in this horizontal surface, is to draw a perpendicular line from the sun to this flat surface. I mean, this line, this is the perpendicular line which comes through the surface of this flat surface this flat surface, and the line that unify us and the position of the sun on the horizontal plane. The line that unifies that is the end line of our azimuth angle. What we will do next is we will start from north as a fixed direction, fixed point. We will start from north and we will go through to that line. The line that unify us and the position of the sun expressed in the horizontal plane. I mean, as you can see in the last image, we start from 0 degree from the north and we are ending in that line that unify us and the position of the sun in the horizontal plane. This is I want to give a concrete example so that we can understand better. Sorry for that. I gave a little break. What was the point that we left? Yes. Lastly, we talked about what is azimuth, what is the sense behind azimuth, and I want to talk a little bit about what is the function of azimuth for solar panels. As we wrote in the slide, as you know, we use azimuth angles to ensure that our panels are facing to the optimal direction in order to capture maximum amount of solar energy throughout the day. And you know, there's a general saying that if you are in the northern hemisphere, your panels should face toward the south, or if you are in the southern hemisphere, your panels should just towards the north. But what is the sense behind this general saying? We can say, as we wrote, in the northern hemisphere, since the path of the sun is predominantly the south of the zenith, so south-facing panels will be optimal in northern hemisphere. But if we are in the southern hemisphere, since the path of the sun is predominantly the north of the zenith, so north-facing panels will be optimal. That is the sense behind it. I mean, that is related to path of the sun, whether it is north of the zenith or south of the zenith. It is related to that. If the sun of the path is predominantly the north of the zenith, then the north-facing panels are optimal. But if the path of the sun is predominantly south of the zenith, then south-facing panels will be optimal. When we come back to our Pvsyst and coming to the point where we calculate the azimuth, as you can see, what we will do, we will calculate the azimuth. We can yes, we can say like that. We will calculate the azimuth of the panels, as you can see in this image, azimuth of the panels for the both side of the ridge of the roof. For the both side of the ridge of the roof, we will calculate for the azimuth for these two opposite side of the roof. But what we will, how we will calculate the azimuth of the panels. In order to calculate the azimuth of the panels, first we should calculate the azimuth of the building. But how we will calculate? Surely we will benefit from Google Earth again. What we will do, we will make a click to ruler, we will choose line, and after choosing line, what was that line? This was the line that intersect two roofs. This was the intersection line. From the beginning point of the intersection line, we should draw a line, and we will look at the heading. In the heading, what we will say, it is approximately the 305.82 degree. Roughly, it is 306 degree. In order to verify that, we can go to one ridge of the one roof, and we will calculate again the heading as the heading of the roof is approximately 306 degree, and when we go to another ridge of the roof, it will again be correspond to 306 degree approximately. What we can understand from that, in the Google Earth, according to Google Earth, or roof azimuth, or building azimuth is approximately roughly 306 degree. But there is a crucial point that we are not able to take this 360 and totally paste to Pvsyst. What is the explanation behind it is that because the coordinate system of the Google Earth and the coordinate system of the Pvsyst is different from each other. Because of these differences, we should make some angle conversion between Google Earth and Pvsyst so that we can make the angle that we found in the Google Earth will be adjustable to the Pvsyst. How we can calculate for this? How we can understand these calculation steps? First, we should understand the sense behind the Google Earth coordinate system and Pvsyst coordinate system. As you can see in the Google Earth coordinate system, it starts from the 0 degree, it goes from 90, 180, 270, and it completes itself to the 360 degree. But when we come to the Pvsyst coordinate system, it starts from 0, or in another name, start from 100, minus, for example, minus 180 degree, and it completes itself to the 180 degree. I mean, it is not completing itself to 360 degree, just like in the Google Earth. So there is a confliction within that coordinate system. What we will do, we will do some angle conversion so that they will be adjustable. I mean, the angle will be adjustable for the Pvsyst. What we will do? Firstly, how can I say, the angle that we found previously, what we found 360 degree in the Google Earth is the azimuth of the roof, azimuth of the building. What we will do first, we will convert the azimuth angle of the roof to the Pvsyst. I mean, we will make the conversion that we can use this angle in the Pvsyst, and then we use this converted angle, and then we will calculate the azimuth of the panels according to this converted angle from the Google Earth. I mean, we will calculate the azimuth of the panels from the azimuth of the building, that is, and this is the angle that we convert from the Google Earth. Let's try to understand the rules. What is the conversion rules? As you can see, this is the coordinate system of the Pvsyst. What we will say, we have at most 180 degree, and we have at least minus 180 degree. The angles, what we will say, the angles that is greater than 180 degree and the angles that is less than minus 180 degree is not acceptable in the Pvsyst. What we will do, if we attain an angles in the Google Earth that is greater than 180 degree, it is not acceptable for us. We will do some conversion. If we encounter, there is no saying that if we encounter with the angles that is less than minus 180 degree, because in Google Earth, we are not dealing with the minus degrees. I mean, we are not dealing with the negative degrees. In the Google Earth, we are just dealing with positive degrees. As you can see, it starts from 0 and it's all have positive angles. So when we are calculating, firstly, the azimuth of our roof, the azimuth of our building, we are in Google Earth. We are not dealing with the negative angles. We are just dealing with the positive angles. And what was the crucial point? If we attain an angle that is greater than 180 degree, we will do some conversions. For example, if the angle in the Google Earth, we can look that part. If the angle in the Google Earth, for example, that angle will be X, is less than 180 degree, what we will say? We will say that we are in a safe region, or angle that we found in the Google Earth is less than 180 degrees. So we can use exactly that angle in the Pvsyst. Yeah, this angle is compatible that we can use in Pvsyst safely. If we attain, for example, 120 degree in Pvsyst for the azimuth of the roof, then we can safely say that it is also acceptable in the Pvsyst because the angle is less than 180 degree. But if we attain an angle in the Google Earth that is greater than 180 degree, what we will do? What will be the azimuth of the roof? We will subtract the minus 360 degree from the angle that we found in the Google Earth as the azimuth of the roof. For example, in order to make a concrete example, let's say we found 360 degree in Google Earth for the azimuth of the roof. What we will say, oh, this angle is greater than 180 degree. What we will do? We will subtract 360 degree from that, and we will attain minus 54 for the azimuth of our roof. But if we minus 54 or for our azimuth of the roof. And also another example, Another example, for example, we attain the 190 degree for the azimuth of our route in Google Earth. What we will say, oh, this angle is greater than 180 degree. What I have to do, I have to subtract minus 360 degree from that angle, and what we will attain? We will attain minus 170 degree as the azimuth of the building in the Pvsyst. Okay, these left rules are the rules that we will use to convert the azimuth of the roof from Google Earth to Pvsyst. But we are not completing yet. What we will do? We will find the azimuth of our panels. It is important point. Our actual aim is to find the azimuth of our panels on the both sides of the ridge of the roof. Our actual aim is that. What we will do? Actually, in that point, the placement of the panels is so important. What I mean with that sentence is that, for example, for example, if we are placing our panels, I mean the width of our panels along the ridge of the roof, we say we are making a perpendicular placement. If we can draw like that. If the width of our panels is laying along the ridge of the roof, the width of the panels is laying along the ridge of the roof, then what we will do, what we can say, it is the perpendicular placement. But as you can see from that image, if we are placing our panels or height of our panels along the ridge of the roof, then we will say it is a parallel alignment, parallel placement, actually. What is parallel placement? If the width of the panel, if the height of the panel is placed along the ridge of the roof, then it will a parallel placement. But if the if the width of the panel is placed along the ridge of the roof, then it will a perpendicular replacement. And after knowing that information, we can come to our calculations. In that section, since we are dealing in this section, we will write the azimuth of our panels. Since we will write the azimuth of the panels for the orientation 1 and orientation 2, I mean the both sides of the roof that have two opposite tilts, we should actually know what will be our placement type. I mean, we should look from a file to understand what is the replacement of our panels. They can be a parallel placement, it can be a perpendicular placement. For that, if we are working for a company, generally, we will a cat file for the how can I say, the placement of the panels. For example, for our 2 tilted rooftop solar power plant system, we draw a panel placement like that, as you can see, this line is the one ridge of our roof. This is the another ridge of our roof, and this is the intersection point. This green line is the intersection point of our two roof. And how we can understand what is the placement type of our panels? As you can see, the width of our panels is placed along the ridge of the roof. And since the width of the panels is laid along the ridge of the roof, what we will say, it is a perpendicular placement. If it is a perpendicular placement, what we will do, we will add 90 degree and subtract the 90 degree from the angle that we found for the azimuth of the building, azimuth of the roof in the Pvsyst. But if it is a parallel placement, if it is a placement just like in that scenario, then we will not add 90 degree or subtract the 90 degree, because there is no perpendicular situation between the panel placement and the ridge of the roof. We will just place our panels parallel to our ridge of the roof. There is no addition and subtraction 90 degree for that, for that situation. But in our case, since in our AutoCAD file, for the placement of the roofs, we have the perpendicular placement. What we will do, we will add 90 degree and subtract 90 degree for the angle that we found in found in Google Earth, and then convert in Pvsyst as the azimuth of our building. Let's come to the rules again. For example, what we wrote. Let's say we wrote the azimuth of our roof is calculated as minus 54 degree. This is the converted version from Google Earth to Pvsyst. It is found as minus 54 degree. And also it is for our project. This is the exact value for our project. What we will do, since we are in perpendicular placement, we will add 90 degree and subtract 90 degree. When we add 90 degree, we will attain 36 degree. When we subtract 90 degree, we will attain minus 144 degree. And since this 2 degree that we attain is less than 180 degree, or since they are not less than minus 180 degree, I'm saying that sentence because, as you remember, in the Google Earth calculations, for the Google Earth calculations for the azimuth of the roof, I said that we are not worrying about the negative degrees, but when we are in a Pvsyst environment, we are curious about the negative degrees. Because of that, we should ask ourselves two questions. If the angle that we attain is greater than 180 degree or less than 180 degree, the both degrees that we will attain is not greater than 180 degree or less than minus 180 degree, then we are in a safe region. The first azimuth of, the panels that is positioned on the one side, one side of the ridge of the roof will be 36 degree, and the panels that is placed another opposite side of the ridge of the roof will be minus 144 degree. But when we encounter with another example, let's assume that just like in our previous example, assume that we found Google Earth 120 degree for the azimuth of the roof. What we will say, there is no confliction with that angle. we can just safely say that in a same manner or azimuth for our roof will be in Pvsyst exactly 120 degree because we are in less than 180 degree. When we come to the point where we calculate the panel azimuth, what we will do, we will add 90 degree. We will add then 210 degree for a azimuth of the panel that is placed one side of the ridge of the roof. We will ask ourselves, is it acceptable degree for ourselves? No, it is greater than 180 degree. What we will do? We will subtract 360 degree as our general rule. And we will attain minus 150 degree, which is acceptable. And we add the 90 degree and we attain as a result as minus 150. But also at the same time, we have to subtract 90 degree. We will attain 30 degree directly. And there is no problem with that angle. We don't worry about the conversion of it because it is both less than 180 degree. It is both less than 180 degree. And it is also is not less than minus 180 degree. Or for another example, as we did in that example, as you can see, for example, we can find the azimuth of our roof in the Google Earth as 190 degree. What we will say it's greater than 180 degree. We will have to subtract the 360 degree from that and we will attain minus 170 degree for the Pvsyst or the azimuth of the roof. But we are curious about the azimuth of the panels. What we will do, we will add 90 degree and subtract 90 degree from that angle. From the angle of the azimuth of the roof for that is calculated for Pvsyst. When we add 90 degree, we will attain minus 80 degree. We have to ask ourselves, is this angle is greater than 190 degree? No. Is this angle is less than minus 180 degree? No. Okay, we are in safe region. But when we are subtracting the 90 degree from minus 170, we will attain minus 260. We have to again ask ourselves, is our angle is greater than 180 degree? No, but is this angle is less than minus 180 degree? Yes, since it is not allowed. I mean, since in the Pvsyst we are not acceptable with the angles that is less than the minus 180 degree, what we will do now, as you can understand from that rule, we will attain 360 degree to the angle that we attain. What we will do, since we are less than minus 180, we will add I wrote wrongly. It should be minus 260 plus 360. We will attain 100 degree. There is a typo here. It should be minus 260 plus 330. We will attain 100 degree for or for the angle or the azimuth angle of the panel for the one side of the ridge of the roof. This was the angles like that. And for our project, what we will write? We will write 36 degree for orientation 1 and minus 144 degree for the orientation 2. Let's write 36 degree for the one orientation and minus 144 degree, minus 144 degree for the another orientation. And There's a trick for in that how can I say, in that part. When you click the orientation 1 azimuth, and when you click the orientation 2 azimuth, as you can see, they are the reflection of itself. If they are the reflection of itself, we calculated the angles correctly, because what we will say in the beginning, we are dealing with the opposite sides. I mean, there is one ridge, but the sides, the tilt, the angles of the sides of the ridge are opposite to each other. And when we do this move and we face with the reflection, we can say that yes, we calculated the angles correctly, and we will click OK in that scenario. Okay. Okay. And this was the orientation part. But before the moving to system part, we should surely save our project. We should again save our project from the top button and from the below button, and in our another video we will move forward with the system part. I know the explanation for the calculating the azimuth angle, I mean converting the angles from Google Earth to Pvsyst, finding the azimuth of the roof, and then finding the azimuth of the panels is a little bit long. But if we learn that rules and digest these rules comprehensively, this will be easy for us for another projects to calculate the azimuth value for the rooftop systems. It will be easy for us if we digest the sense of it. Thank you very much for listening to me this long video. See you again.